Weber. Very simple problems, but you must be familiar with solving these kind of problems. Alright, let's now talk about Faraday's law of electromagnetic induction. Faraday's laws of electromagnetic induction gives us an idea of how much is the induced EMF and in what direction does it take place. So if you can answer these two questions, that will explain Faraday's laws of electromagnetic induction. Well, Faraday's investigation on electromagnetic induction showed that the magnitude of the induced EMF E is equal to the rate of change of magnetic flux. In other words, if the magnetic flux changes very fast, the induced EMF will be very high. Now, this gives you only the magnitude of the induced EMF. We can write it as E equal to d phi by dt. The induced EMF is a measure of the rate of change of magnetic flux. The direction of the induced EMF is given by another law called the Lenz's law. Lenz's law. Now, the induced EMF causes a current to flow in the conductor. Is that right? Yes. But whenever there is a current flowing in a conductor, that current will produce a magnetic field. Now, remember now, there are two magnetic fields. What are the two magnetic fields? One is the original magnetic field, that is the cause of induction. Once there is induction and a current flows in the conductor, that current will produce another magnetic field. Now, Lenz's law talks about the direction in which the magnetic field created by the induced EMF is. So the induced EMF causes a current to flow in the conductor, and this current will produce a magnetic field which will oppose the changing magnetic field that is the cause of induction. In fact, Lenz's law says induced EMF is in such a direction as to oppose the very cause of it. What does that mean? Now, did you understand what I'm talking about? Well, we know that when a magnet is brought closer to a conductor, the magnetic flux linked with the conductor increases, right? Now, that increase in magnetic flux will induce a current in this conductor, and that induced current will produce a magnetic field which will oppose the increasing magnetic field. That's what it means. So, if the induced EMF is due to an increasing magnetic field, the induced current will be such that the magnetic field produced by that current will oppose that increasing magnetic flux. On the other hand, if the induced current is caused by a decreasing magnetic field, the direction of the current will be such so that the magnetic field produced by that current will oppose that decreasing magnetic field. That is the meaning of this. So, this current will produce a magnetic field which will oppose the changing magnetic field that is the cause of induction. I'm going to explain that further. In other words, the direction of the induced EMF is such as to oppose the cause of induction. Now, let me take a couple of examples and illustrate it after putting this into an equation. What does that mean? Well, all we need to do to combine the two laws, Faraday's law of electromagnetic induction and Lenz's law together, gives us that equation. E equal to negative d phi by dt. E equal to d phi by dt is Faraday's law, and Lenz's law says the direction of the induced EMF is such as to oppose the cause of induction, and that is indicated by the negative sign. If a coil of N turns is subjected to a changing magnetic flux, the induced EMF will be E equal to negative N d phi by dt. Now this will be the induced EMF in one turn of the coil. If there are n turns of the coil, for example, if you look at this coil that I just showed you, the induced EMF will be greater in this coil than in this, because this contains more number of turns. So E equal to negative n d phi by dt, where n is the number of turns of the coil. Alright, let's now talk about the direction one more time. When the north pole of a magnet is brought towards this conductor in the form of a ring, the flux linked with the conductor increases. Is that right? When the north pole, this is up. When the north pole is brought closer to the conductor, the number of lines of force linked with the conductor will increase, and that increase will produce a current on the conductor, and the magnetic field produced by that conductor will oppose the changing field. Now, if a north pole is brought closer, what kind of a pole on this side of the conductor will oppose the coming north pole? It has to be a north pole itself, isn't it? Only a north pole can oppose a north pole. That means if a north pole is moved towards this conductor, then this end of the conductor will become a north pole. Now remember, how do you know? In the last lesson I told you, in the case of a solenoid, if you look into the solenoid and if the current flows in the counterclockwise direction, then that end will be a north pole. If the current flows in the clockwise direction, that end will be a south pole. So, if the induced EMF has to oppose the increasing magnetic flux there, that means the induced current should produce a north pole here. Or, if I look from this end, the current must flow in the counterclockwise direction. So when the north pole of a magnet is brought towards this conductor, the current, the induced current will be in the counterclockwise direction. Right? Now, that means this is the induced current, and the magnetic field produced by the induced current will be then this. And this magnetic field will oppose this increasing magnetic field. That is what Lenz's law says. Now tell me, if the north pole is moved away, what would be the situation? Well, when the north pole is moved away, then the magnetic flux linked with the conductor decreases, and the direction of the induced current will be such as to oppose the decreasing magnetic flux. Now the only way to oppose a magnetic field due to a north pole is to produce a south pole. That means if there is a south pole there, the south pole and the north pole should strengthen. That strengthening will oppose the decreasing magnetic field. So when a north pole is pulled away, the direction of the induced EMF produces a south pole here, so that the two magnetic fields are in the same direction, so that they add up, that way opposing the cause of that induction. Alright, I want you to look at these two one more time to make sure that you understand it. Now, one more time, when the north pole is moved towards the conductor, the magnetic flux linked with the conductor increases, and that increase will induce a current, and the magnetic field produced by the induced current will oppose the increasing magnetic flux. That means there must be a north pole created here. And the north pole can be created only if the direction of the induced current is counterclockwise. When a north pole is moved away, the magnetic flux linked with the conductor decreases. And that decrease in magnetic flux will induce a current here, which will oppose the decreasing magnetic field. the only way to oppose the decreasing magnetic field due to a north pole moving away is to create a south pole there. That means the direction of the induced current will be now clockwise. So when the north pole is moved towards the conductor, if the direction of the induced current is counterclockwise, when it is moved away, the current will be clockwise. The direction of the current changes. Now the magnetic flux linked with a conductor can also be changed by turning on or off an electric circuit kept near it. Well, that is an important part, and you must actually pay attention to it. Now here I have this coil of wire that is connected to this battery. In fact, I have connected one wire, and I will connect the other wire later on. And another coil over here, I'm going to put it inside. Remember, they are not making contact. And this second coil is connected to a galvanometer. Now, I'm going to pass a current through the first coil by connecting it to this battery, and I want to watch. Remember, the galvanometer is not connected to the first coil, it's only connected to the second coil, this one. It is only connected to that galvanometer. Now, watch what happens when I connect this first coil to the battery. Now, look at that galvanometer. It's jumping. Now, what is happening? When a current flows in the outer coil, it produces a magnetic field, and the inner coil is inside the magnetic field of that coil. Now, what happens is, when I turn the current on, the magnetic field produced by this current increases. It is that increase in magnetic flux that produces that induced EMF in there. And when the current is turned off, during that time, the magnetic field decreases. So both times turn on and turn off, on, off, on, off, on, off. You can see during the time it is on, the reflection is one side. When it's turned off, it is the other side. Once again, on, off, on, off. Alright. So when the current in this coil is turned on, that increasing magnetic flux will induce a current in this coil. Also, when the current is turned off, there will be a similar induction. So when the switch is turned on, the current grows from 0 to a maximum value in there, and the associated magnetic field also grows from 0 to a maximum. Here, this is the magnetic field. The current in this conductor grows from 0 to a maximum. That means the magnetic flux generated by that will also grow from 0 to a maximum. So this conductor is now subjected to that increasing magnetic flux. That will generate an induced EMF in this conductor. So this increase in the B will induce an EMF in the ring. Same way, when the switch is turned off, the current decays from, look at this, during the time the current remains stationary, there is a magnetic flux, but there is no change in magnetic flux. So if the current remains stationary, there will be no induced EMF. The induced EMF occurs only during the time, that very small instant when the switch is on, the current grows to a maximum, or when the switch is turned off, the current decays from a maximum to 0, the magnetic flux also decays from maximum to 0, and that decrease in magnetic flux will induce an EMF. So the associated magnetic flux also decays from maximum to 0, and this decrease in the B field will induce an EMF in the ring. Now, you notice that if the current flows in the clockwise direction, if the current grows in the clockwise direction in this coil, the induced